center, we also find a magnet at the center which is rotating. The magnet has a north and south pole, or you can think of it as a positive and a negative half. The electrons in the wire are negatively charged. As you might already know, magnets push or pull depending on the polarity. So as the magnets rotate past the coil, the positive and the negative half are going to therefore push and pull the electrons within the copper coils and also through the connected copper wires. The magnetic field of the magnet varies in intensity. So as the magnet rotates past the coil will experience a change in intensity of the magnetic field. This will be from 0 up to its maximum intensity, and then as it passes the coil, it will decrease again back to 0. Then the negative half comes in and pulls the electrons backwards with the same change in intensity. Each full rotation of the magnet will therefore produce this wave pattern known as a sine wave. The voltage is not constant in this type of electricity. Instead, it repeatedly moves from 0 up to its peak, back to 0, then to the negative peak, and then finally back to 0 again. Frequency refers to how many times this AC sine wave repeats per second. In North America and a few other parts of the world, we find 60 Hz electricity, which means the sine wave repeats 60 times per second. And as each wave has a positive and a negative half, this means its polarity will therefore reverse 120 times per second. In the rest of the world, we mostly find 50 Hz electricity. So the sine wave repeats 50 times per second, and therefore the current reverses 100 times per second. We also have single-phase as well as three-phase AC electricity. Most homes around the world use single-phase electricity. Large commercial buildings, as well as some homes, especially in Europe, will use three-phase electricity. Homes in North America use split-phase electricity, where a center tap transformer splits a single phase into two, which provides two hot wires and a neutral. We've covered how split phase electricity works in detail in our previous video. Do check that out, links down below. With single phase, we have a connection to just a single phase from a generator, so we have just one sine wave. But with three-phase electricity, we have a connection to each of the three phases. The phases are coils of wire which are inserted into the generator 120 degrees apart from the previous. This means the coils experience the peak of the rotating magnetic field at different times. And it's this that gives us our three phases, each with a different sine wave that is slightly out of sync from the previous. Remember, electricity wants to get back to its source in a complete circuit. As the current is flowing forwards and backwards at different times in each of the phases, we can essentially connect the phases together, and the current will move between the different phases as the polarity of each phase moves forwards and backwards at different times. Any excess will flow in the neutral back to the source if needed, but that's only if the load on any of the phases is unbalanced. With single phase, we have these large gaps between the peaks, but with three phase, these can be combined to fill in the gaps and therefore deliver more power. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now, and I'll catch you.
A little bit later, I got several of these that we're going to be doing because this particular module, as I've told you before, is this is going to be that one that's difficult for me. It's the most difficult of the class as far as getting into the details of it. So we will be taking our time. In fact, I'm going to have to sit for some of it, and I'll be up and down while we do this. Module 1 in your electrical 2 books, and you've got your study guides out. Let me get this screen cut off because I'm going to do some drawing. All right, I'm pretty sure. All right, how many of y'all got a head start and already, how many of you have completed the study guide or got at least 50% through it so far as a head start? Okay. So you're somewhat comfortable with the sine waves and everything? Who's comprehending what's happening with the AC current? Yay, nay? Yes, no? All right, let's get right at the start of this unit, okay? We got a activity you're going to be doing. By the time we get to the end, you're going to be getting your voltage meters. we're gonna be taking actual voltage readings, and then you're gonna be finding out what the peak values were based on those voltage readings, all right? So you and your teammates are gonna take several different voltage readings, come up with an average, and then we're gonna apply and find our maximum peak voltage on that AC wave based on the readings that you get with your meter, okay? All right. So some of the terms we're gonna be covering: frequency, hertz, peak voltage, radian, root mean squared. Frequency, the video we just watched kind of wrapped up at the end of it. What does the frequency cover? Let me get y'all, let me hear you awake and read. It's the number of cycles what? Y'all with me?
Alternating
The number of cycles that an alternating electric current sound wave or a vibrating object undergoes per second. So we count frequency in seconds, right? The number of times it rotates. For AC voltage, we're looking at this. We've got our sine wave, right? That one's dead. This one ain't much better. Do I have a marker up there on my desk?
Yeah, good catch.
That's probably the good one. Oh yeah, much better. All right, so we talked about the sine waves. So from here, 0, that's 90 degrees, right? 180 degrees, 270, and then at 360, right? This represents one cycle, okay, for the AC current. That means it's maximum peak, returns to 0, the minimum peak, and then back. When the AC current does that one time, that is one cycle, okay? We measure the frequency in how many times this happens, this from here to there, right? Because then it's going to continue on, so forth and so on. But each time, one cycle of up and then returning to there, however many times that happens in 1 second is how we're measuring the frequency, and we measure that with what? What's the measurement term we use? Who remembers? Hertz. Right? So in the U.S., who remembers what I told you our most common frequency is in the United States? 60 hertz. So 60 hertz means that this is happening how many times per second? 60 times per second, right? So that means you have 60 cycles per second. Now your study guide starts right off on number 1, and what does it ask us? If it takes 0.2 of a second for one cycle to occur, what is the frequency? C5. Come in. Good. Thank you, Dez. Number 1 asks you the time for one cycle is 0.2, and y'all are correct in saying that it's 1. How can we figure that out? The number of cycles divided by the time. What's 1? What does that equal? What's 1 divided by 0.2?
0.5. No.
What's 1 divided by 0.2?
0.2. 5.
5, thank you. How about if we had said there are 10 cycles every 0.2 seconds. We would put 10 over 0.2,
50.
and we would know it was 50 hertz, right? So you can divide the amount of time per cycle, and that's one way to determine what your frequency is. So your answer on number 1 on that study guide that you were doing, you were correct, is C. What's the second one asked us? What's the frequency of an AC waveform that completes 30 cycles per half second?
Deep. 60 hertz.
60 hertz. What's the easiest way for us to figure that one out? If it's a half a second, we know that we want to measure it in a full second, right? So however many hertz it is in a half second, or how many cycles it is, how do we take it from a half a second to a full second? Just multiply times
2.
right. So if it's doing 30 in a half a second, it's going to do 60 in a full second. If it's doing 50 in a half second, multiply times 2, then it would be 100, okay? All right. Let's look ahead. Root mean squared, that's another one of your trade terms. We're going to get to that. That is the square root of the average of the square of the function taken throughout the period. The root mean squared value of a sinusoidally varying voltage or current is the effective value of the voltage or current. That sounds like a whole lot of a mouthful of stuff, right? What we're going to get to figure out is the root mean square. When you read your meters and we're testing the voltage and stuff, that's basically the reading you're going to be getting. It's going to be giving you a voltage reading. When you're reading AC voltage, you're reading on that meter basically the root mean square of that AC waveform, right? Because what are the differences? Let's make sure we're clear. What are the differences we talked about with DC voltage? DC voltage is just traveling in a direct line, right? That's why it's called direct current. All right? It's flowing from negative to positive. It's flowing through that line. AC voltage is doing this, right? And it's actually pulsing, but it's cycling. And that directional flow is changing constantly. In fact, at 60 hertz, that directional flow is doing what? How many times is it changing per minute at 60 hertz?
120.
120. Right. The directional flow is going to change twice per cycle, right? Because each cycle, your direction flows here to maximum peak, then it goes there and it comes back. So at 60 hertz, that means in 1 second, the directional flow of those electrons are reversing 120 times. Basically giving that pulse. That's what the AC current is doing, right? So when you saw in the video and it was showing them going like this, so you can visualize it, that's really good, but that's actually happening 120 times a second, right? In the ballast coming off of these fluorescent lights, what did we say some of the frequencies get changed to there? Anybody remember? Last week when we were doing electrical lighting? Remember I said that their ballast changes the frequency from the 60 hertz that we normally operate to what comes off and goes to those fluorescent tubes. Anybody remember those numbers? Like 20,000 or more, right? And remember when I pulled out and demonstrated how you could barely, if we got it back, you could barely see and it's pulsing? That's why the light looks like it's static to us. But actually that light is pulsing over, with a frequency of over 20,000 pulses per second. Because that's the frequency. All right? That's so quick we see it as static until one of them starts to go bad. Then when they start to go bad, what do we see? Start to see that waving, right? That means that the frequency is starting to fluctuate off of pattern, and that's why we can visualize it then. So, just don't let some of the terminology freak you out. We're going to get into how it can sound a lot more daunting than what it really is. Okay? So the goal is we take these very daunting sounding things and these highly technical aspects and we get it into a workability that we're going to be able to work with and function with, all right? Check out peak voltage in that trade term, because we're going to talk about that here shortly. The peak value of a sinusoidally varying voltage, cyclical voltage, or current is equal to the root mean square value multiplied by the square root of 2. Now we know the square root of 2 is what?
1, 2, 2.
No, square root of 2.
4, 1.2. 1.
1 times 1 equals what?
2.
1.
So it can't be the square root of 2, right? Square root of 2 is 1.414, so forth, so on. You multiply 1.414 times that, you're going to roughly get right at 2. Okay? AC voltages are usually expressed as RMS values. That's what I was just talking about. So you're going to have your 120, 208, 240, 277, your 480. All of those are your RMS or your root mean square values. All right? The peak voltage differs from that. For example, the peak value of 120 volts is actually 120 times 1.414. And that equals what? 170 volts, right? That's what you're going to actually be doing when we conduct our test. You're going to take actual voltage readings properly with the meters, record them, and then you'll average out the different voltage readings at different locations, come up with an average RMS voltage, and then you're going to determine what the overall peak voltage values are for that sine wave for the AC that we have going through our classroom and surrounding area. All right? So we're going to apply these principles to a real life deal and then understanding where those readings are coming from. All right, they talked about the AC voltage in the video. I want to make sure y'all got that. We'll come back to this sine wave a little bit later. Y'all know my drawing is not all that great. Who really understood what they were talking about and how the magnets work?
No.
Let's break that down a little bit, because that's key. So, we've got our line here, a copper wire. Okay? And we got electrons in here. They're just all over the place. Bigger the wire, the more electrons we'll have, right? The more electrons we have, the more current capability and flow that we have. All right. With DC power, DC current, okay, you would have a negative flow returning to the positive. What do we know about like forces? Let's say we got two magnets here. That's the North Pole and the South Pole. If I drew one right here, just like that, what are those magnets going to try to do?
Connect.
They're going to try to come together, right?
Mm-hmm.
Why? Because,
Opposite attract.
Because they're magnets.
right. So if we just said that's a positive and a negative, and that's a positive and a negative, right here, that negative is going to try to move to that positive, correct? How many of y'all ever played with a magnet and then you got some of them and you put them close together and then they push themselves away? They repelled each other, right? That meant that we had, and we'll just go with the same positive and negative, and then we had this one turned this way. When we get this, that's when they push away from each other, right? All right. See, now in modern times, we're starting to figure out how to utilize that to move around, like magnetic propulsion. Okay? Electromagnetic motors work like this too. You ever seen these electric trains and different things like that? If you charge the rails with a certain charge at a certain pulse, that is the same charge that you're applying with the train, it'll propulse and it'll just shoot right down the track. right? And all you're doing is basically controlling the charge of the magnetic fields. So it can be a very low energy effective way of transportation that really, you're not powering the train, you're just powering the magnetic charge, right? So, but this is how electricity works at its most basic kind of fundamental way. So we know we've got copper wire and we've got electrons in there, right? How do we make those electrons move? What is the charge of the electrons? In an atom, at the atomic structure, protons have what type of charge? Electrons have what type of charge?
Negative.
So the electrons are already negatively charged, right? So if we set the magnet and we put the negative end of that magnet there and the positive end there, which way are those electrons going to go in reaction? The electrons are going to go away from that negative charge, right? They're going to start moving this way. Got it? How about if that's reversed? Now they're going to try to come this way, right? What happens if the magnet's sitting like this? They're static, right? They're holding for a second. Let me negative, positive on the back of my remote. Let's visualize what's happening. Negative, I better do this with both hands. There's my magnet, negative charge, what's happening? Now if I figure out a way to spin this, as this negative moves away, when this is here, they're at maximum speed in that direction, right? As it starts to move away, they're still moving that way, but they're slowing down, and now they stop. But now as they come, guess what they're getting ready to do? They're starting to come back this way. And they're going to come back this way for this entire cycle until it gets to here, and now they're starting to go back. Does that help y'all visualize that as that's turning? Now this is going to turn how many times a second to give us that cycle frequency? How many times does this turn? If I want 60 hertz, how many times is this going to complete a 360 degree rotation?
60.
Per second?
60.
120. Because it's going to do, well, it's going to flip the direction 120. You're right, it's going to do a complete loop 60 times. I apologize. But it's going to reverse that direction 120 times, right? So I'm not going to get up here and try to spin it that fast, right? Does that help with the visualization? All right? So what we're doing is we're moving that. That directional flow is represented, we're at 0. And this hopefully make sense. This is what we're seeing when we're seeing that sine wave, right? Let's start it at 0. You ready? We're at 0. Boom, 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 boom. Maximum at 90 degrees. Okay? And how far have we rotated? 90 degrees, right? Now, we're still on the positive side, but we're slowing down until we get to that 0 state again, right? So this is all you're witnessing right here, and now we're at 180 degrees, because we've rotated at 180 degrees, right? Now it's coming, we still got movement, but now it's moving the other direction. It's coming back towards us now, right? Until it gets to there, at 270, which would be our minimum peak. Now, the flow of electricity right here is the same this direction as it was here as far as going that way. The intensity is the same. This is our maximum peak and our minimum peak value, okay? But whatever the current flow is here, let's say we're running 30 amps here. Here you're also running 30 amps. Now the actual meter that was reading it would show that negative, right? Because it's on the other side of the wave. But it doesn't mean you're running less than zero. That negative doesn't mean less than zero. That negative is referring to the direction. So when you get a voltage reading, right, if you're reading certain things, and you, especially ampacity, and if you're reading it on a cycle wave, don't let that positive negative, you're not going to have negative voltage, right? It'll just be current or voltage on the opposite side or on the downside of the sine wave. But it's still doing 30 amps worth of work. Does that help? Is everybody following me? Yay, nay. You with me, Nas? Okay. And then we rotate finally back this way, and it gets us back to there, and that cycle is just going to continue on again. And each time that's happening. So that's what we're looking at today, right? We're going to expand and get a lot deeper into finding out what certain values are at any point, right? Like at 30 degrees, if you wanted to find out what the value was at that 47 degree point, we'll talk about that, but we're not getting into that today. That'll be more tomorrow, okay? But the way we'll do that is we're just going to apply the sine value. And some of y'all, most of y'all should remember that from some level of math, right? Where you're trying to find the sine of a certain angle. Yay, nay?
Yeah.
What's the sine of 90 degrees?
30.
All right, we'll work on that tomorrow then. Let's focus on where we're going with it today. So, do what?
No.
So number 3 asks you if the phase angles of two sine waves are both 0 degrees, then the waves are what? Now that's found in section 1.2.0.
They are.
How many of y'all found that?
D.
They are in phase, right? If the angles of both sine waves are both 0 degrees, they're in phase. If one's 0 and one's at 90 or 270, they're out of phase. All right, so let's look at some peak voltage stuff, because we're talking about when we're at those points. Number 4 in your study guide digs right into it. A circuit has a peak voltage of 310 volts. What is the average voltage value?
192.
All right, so where on this sine wave, first of all, would my peak voltage be?
90 or 270. 90 or 270.
Let's go at 90. Correct. And we said, and what did they ask us? What's the voltage at peak?
310.
310. So if our voltage at that point is 310, they're wanting to know that's the maximum peak voltage, right? That means this circuit is putting out 310 volts of potential energy at the peak of its sine wave. Coming up, it's increasing to 310, now it's decreasing back to 0 and then to negative and back up, right? How do we determine what the average voltage value is going to be? In other words, if we went up to this circuit, we put a meter on it, what reading is it going to give us? What do we use? Go to section 1.1.5. Average value. Miguel, what you got on that? The average value is calculated from all the values in the sine wave for one alternation or half cycle.
Yeah.
Half cycle is used for the average over that. if the sine values for all angles up to 180 and one alternation are added and then divided by the number of those values, the average in that example will equal 0.637. So y'all gonna wanna write this down and know that this is your determinant. Well, what they're looking at here is, if you took the readings, if you wanted to take the time, however many readings that you wanted to take along this curve, you could take 10,000 different readings, every tenth of a degree or however much you wanted to do along that curve. If you took all of those readings, added them up, and then divided them by the number of readings you did, that's going to be your answer, 0.637. Yeah, section 1.1.5. Not in the construction core book though.
I'll probably put it up.
Sweet Jesus. This is what happens coming back from a 3-day weekend.
No, I literally had it on my desk. I don't know what happens with it.
No, seriously, this is what happens when we get a 3-day weekend. Everybody comes back and it's like, oh, we forgot how to function. That's all right. Go ahead and get with it. Get caught up. So if we know that that's 0.637, how do we apply that 0.637 to the question that they're asking? We've got the peak value, 310. We want to know what the average voltage value is going to be, right? And that's going to be what? Let's take that 310 and multiply it times 0.637. Y'all use your technological wizardry over there and tell me what you come up with.
197.47.
197.47? Right. That would be the average voltage. That means if you came to this circuit, forget about the peak voltage, if you were just testing the voltage on it, the reading that your meter's going to give you is going to be what? Are you going to read that 310 or are you going to read 197? You're going to read 197. The reason is the meters you're going to use today and most multimeters, they're programmed in to where that meter is getting that reading of that peak voltage, is getting all of that, but it automatically goes ahead and does this multiplying factor and then presents you with a number that's going to be in that average range. And it's all tied back to give you the equivalent of the amount of heat energy generated and done by that same voltage or that same percentage of voltage in DC. All right? So now, number 5, what does it ask?
A.
Yeah, that gets back into some basic stuff, right?
Yeah.
Who had an issue with that? Circuit resistance of 20 ohms, voltage of 240. How did y'all get to A?
240 divided by 12.
And you got
No.
240 divided by 20, right?
Yeah.
And you got 12. Right? It's going to give you the effective value, and it's going to be equivalent to the same amount of energy transfer in current that's in DC voltage, right? With direct current, we can easily read that. AC current reading the voltage is quite a bit different because there's never a static amount of voltage. It's always going up or down on that wave, right? So we have to figure it out down to an average point. So that root mean square, or the effective value, is what we're looking for. By averaging the heating effects of all the instantaneous values during one cycle, all right, we're over on the second column there, it's possible to find the average heat produced by the AC current during that cycle. the amount of DC that's required to produce that same heat is going to be equal to the effective value of the alternating current. All right? Everybody with me? The most common method of specifying the amount of a sine wave is by stating its value at 45 degrees. Where would that be at? Where would 45 be at here?
Half of 90.
Right. All right. So at 45 degrees, and the value at that point is 70.7% of the peak. Now, don't get confused and think that because we're at 45 degrees, it should be half, right? Because if we were to draw a straight line up here, we're at 45 because of the curve, and because it's gradually slowing down on the curve, if you went across here, that would be 70.7% of the peak value. Y'all see where that happens at there? All right? So it's at the 45 degree mark. So your RMS is going to equal 0.707, because if we convert 70.7 to a percentage, it becomes what? 0.707 times peak value. Got it? And that's going to be your root mean squared. Any questions? That is what you're going to be using to determine the peak value here, okay? Let's look at it from the opposite angle though.
No way.
Let's take 170 degrees before I turn you loose here. I mean 170 volts. Let me write that better. 170 volts. All right, what would be the RMS for 170 volts? We're going to multiply times what? 0.707. 120.19. Right, so 0.707 times that 170 gives you 120.19 volts would be the RMS. Take 122, let me back up. Take 120 volts and now divide it by 0.707.
169.731.
Okay. Now, you said 120.19. Put it back in with 120.19 and divide by 0.707. So 120 divided by 0.707 gives you the peak voltage. All right? All you teams remember that?
You said what?
0.707 is the number you're going to want to know as we go into this project, or this little activity. And you're going to want to know, do I need to divide by that or multiply by that? Any questions?
No, sir.
All right, let's get to the activity here. So each of your teams are going to have a meter. And we're getting ready to take some voltage readings. Each team has 1 meter. And you're also going to need somebody that's going to be doing the recording. Get you a lot of different numbers and dials. Right, where's your teammate? Has he got your meter over there? So how can you look at it? Come on, y'all swing around this way a little bit. Now you see 2 different V's in blue there. There's a V over here. A V over here, right? What's those V's going to stand for?
Volts.
Volts. Which one's going to be the one we're going to be checking with? Which one of those V's?
The one on the right.
Right.
Why the one on the right?
I mean,
What's the symbol beside that V?
those good thing.
The wiggly thing? It's
Yeah.
the sine wave, that's what we've just been talking about, right?
This one.
So you're looking for the volt on there that has that beside it. That means we're gonna be measuring what type of voltage?
Wait.
AC.